Hola. I can't get warm this morning. Wait for a couple more people to get started. I am a little Russian lady. I'm a babushka. Actually, check out. Hey, Bug, come here. Bug. Bug makes just about the cutest babushka ever. Bug! Come here, Bug. Hang on, I gotta get Bug because I gotta show you that he's really cute. Oh, there's Bugger. Okay, come here. Come here. Okay. Let's see. Okay, we're gonna make Babushka Bugger. Yeah. There. Oh, precious little Babushka. Oh, precious little Babushka. You're such a good boy. Yeah. You're such a good Babushka. Good boy. Okay. There you go. All right. Here we go. All right. Cardiff beats Rangers. Okay, class. I'm gonna go ahead and get started. So today's going to be our last day on momentum. There was an issue with one of the questions in the last momentum quiz. I corrected it. So just an FYI. Okay, so what I would like to do is I would like to define something called impulse. Okay. Impulse is denoted by J, and it is a vector. Okay. J is a vector. And it's equal to the integral of the force vector, of some force vector with respect to time from t initial to t final. Okay? So this is the definition of impulse. Okay? That is the definition of impulse. Now, the units of impulse are force times time. So Newton seconds are the units of impulse. Okay. Another interpretation of impulse, if you have a force versus time graph, okay, the area under the curve is impulse. Okay, so if you wanted, so these are both different ways you can think about impulse. So that's just a definition. But what is the impulse? Okay. By the way, this is going to be a short lesson today. This is a fairly simple concept. What is the impulse? What does it mean? So to sort of understand what it means, I would like to go to the sneaky form of Newton's second law. So to remind you, the sneaky form of Newton's second law was net force equals the derivative of the momentum with respect to time. Okay? So what I'm now going to do is I'm going to integrate both sides with respect to time from t initial to t final. Okay. So you can see that on the left-hand side, I have the impulse due to the net force. The impulse due to the net force. And on the right-hand side, I'm integrating the derivative of the momentum. Okay? So that means, so when you integrate a derivative, remember, integration is the reverse of a derivative. So you just get back the original function, evaluated at final minus initial. So this is equal to the change in momentum. Okay? So, all right? So, sort of when we think about what is impulse, the impulse due to the net force is equal, and that's important, it's got to be due to the net force, is equal to the change in momentum of the object. Okay? Impulse due to the net force is equal to the change in momentum of the object. So that's really what, most of the time we talk about the impulse due to the net force. What I would like to do is I would just like to talk a little bit about impulse versus work. Okay? So if we think about impulse is a vector. Okay? Impulse is a vector. It's the integral of a vector force. Okay? Work is a scalar. It has no direction. Impulse has a direction. The impulse due to the net force is the change in momentum. The net work is equal to the change in kinetic energy. Okay? Impulse is the area under a force time graph. Work is the area under a force displacement graph, a force position graph. Okay? So they're very similar. They have a lot of similar things, but there are some differences. Okay? Basically, impulse is to momentum what work is to energy. Okay? So you got to be careful not to mix these two things up. So let's do some examples. First example is let's just calculate impulse. Okay, a force given by f of t equals 4t squared I hat minus 7t j hat acts from 0 to 1 second. Calculate the impulse. Okay, so the reason that I'm doing this example is because I want to just briefly go over how to integrate a vector. So the way that you integrate a vector is you integrate both of its components. Okay, so if I do the integral of force with respect to time from 0 to 1, that would be the impulse. Okay. All right. And so that's going to be the integral of the I component from 0 to 1 plus the integral of the J component from 0 to 1. Okay, so we just integrate the I component and we integrate the J component. And I and J are constant vectors, so they get factored out. I'm going to do these integrals really quickly. So this one is going to be 4t cubed over 3 evaluated from 0 to 1. This one is going to be minus 7t squared over 2 evaluated from 0 to 1. And then remember when we do the definite integrals, it's we plug in the top number and we plug in the bottom number and we subtract them. So this ends up being 4/3 I hat minus 7/2 j hat, and that's measured in Newton seconds. So this is our answer. And we could put that into decimals if we wanted to. All right. Ooh, it's windy. It just felt today like the seasons just all of a sudden changed. Let's do another example. Let's suppose let's say a 3 kilogram object with velocity 9 meters per second east experiences an impulse of let's say 40 Newton seconds in the northward direction. And furthermore, let's say that that is the net impulse. What is the speed after? All right. So that's the net impulse. So first of all, the impulse due to the net force is going to be 40 times j hat, because I'm taking north, south, west, east. So the j direction is northward. The initial momentum is going to be 3 times 9, so that's 27 in the eastward direction. So that's in the I hat direction. So notice how the impulse and the momentum are perpendicular to each other. Okay. The final momentum is going to be mass times whatever the final velocity is. Okay. So now we use the fact that the impulse due to the net force is equal to the change in momentum of the object. Change in momentum is final momentum minus initial momentum. Net impulse is 40 J. So now what I do is I add this over to the other side. So I have 27I plus 40J is 3V final. Then I'm going to divide both sides of this equation by 3. So I get 9I. 40 over 3 is what? 13.3 plus 13.3J. So that's our final velocity. Now we want what is the speed after. So we have this velocity that goes over 9 and it goes up 13.3, and the speed is the Pythagorean theorem on that. So it's going to be square root of 9 squared plus 13.3 squared. All right, which I will plug into the calculator. And we get right about 16 meters per second. Is our final speed. All right? So that's a great example of a impulse problem. Let's do one more example. So let's suppose we have a force time graph. And this is a net force versus time graph. All right? And let's say that the force ramps up and then drops to 0. The peak value of the force is 100 newtons. The time at which the force goes to 0 is 3 seconds. Okay? This net force acts on a, let's say, a 4 kilogram particle initially at rest. Okay? acts on a 4 kilogram particle initially at rest. Okay. There's a question in the chat about why is this minus 27i? It's because its change in momentum is final momentum minus initial momentum. So I have to subtract that 27i. Okay, so first of all, let's calculate the impulse. The impulse is going to be 1/2 base times height. So 1/2 3 times 100. So that impulse is 150 Newton seconds. Okay. 150 Newton seconds. So then I use net impulse is change in momentum. P final minus P initial. Well, because the 4 kilogram particle starts at rest, its initial momentum is 0. And so we just have the final momentum is 4 VF. The impulse is 150. So we divide by 4. That's going to be, what, 75 divided by 2, 37.5 meters per second is the final speed. Boom. Okay. You know what? I'm going to do some more examples. I feel like it. Actually, I'm going to do one more example, and then I have something cool I want to show you. We're going to have a little mathematical digression, and I think you'll enjoy it. Let me have some tea first. Okay, so for this next example, let's suppose we have a ball, and the ball is headed towards the wall like this, okay? And the initial velocity vector of the ball is, let's say, 5i minus 3j. So that's the initial velocity vector of this ball. It bounces off the wall like this, and when it bounces off the wall, its vertical velocity is reversed, okay? But it loses a little bit of vertical velocity because it wasn't a perfectly elastic collision. So we have plus 2i only. And furthermore, friction with the wall slows it down horizontally a little bit. So we have 4 I. All right. So, and these are vectors, my bad. Let's suppose that this is a 2 kilogram particle. And let's suppose that it is in contact with the ground for, let's say, 0.01 seconds. Okay? So how would we determine that? We would have to use, like, a really, really slow motion camera. Okay? But let's just say we have some way of knowing that the time it's in contact with the ground for. Estimate the force of the rocket, I'm already thinking about the next example. Let's estimate the force of the wall, of the ground on the ball. Okay? So this is one of the uses of the sneaky form of Newton's second law. So we have that force, net force, is change in momentum divided by change in time. Okay? Actually, it's the derivative, right? But we can approximate it by a difference, because remember, the derivative is the limit of a difference. Okay? So that's why I say estimate, because we're not literally taking the derivative of the momentum. We just have an initial value and a final value, but we can still approximate it. So the initial momentum is going to be the final momentum is going to be 2 times this vector right here. Okay. So we are going to have 8I plus 4J is the final momentum. The initial momentum is going to be 2 times the initial velocity, so that's going to be 10I minus 6J. And then we're going to divide that by time, so divided by 0.01. So 8I minus 10I is negative 2I. 4J minus 6J is plus 10J. And we divide by 0.01. It's the same thing as multiplying by 100, so we have minus 200I plus 1000J in newtons. So that's our estimate for the force. All right? Okay, so those are some examples with impulse. I'm going to go to my theoretical exposition at this point. All right? And I want to talk about the rocket equation. Okay? I'm going to talk about the rocket equation. So this is a pretty cool equation that we're going to derive. So here's what I want to think about. So here's initial. Initially, the rocket has a velocity v initial. Okay. And it has a mass of m. Okay. And then what does a rocket do as it is? What does a rocket do as it accelerates? Well, it sprays out exhaust. Okay. So afterwards, the rocket now has a velocity v initial plus dv initial. Okay. So dv is the change in velocity. Okay. And it has a mass of m plus dm. Please keep in mind that dm is going to be less than 0 because it actually lost mass. And then it sprayed out the exhaust. Okay. The mass of the exhaust would have to be negative dm. Okay. And the velocity is going to be the initial velocity minus whatever the velocity of the exhaust is. Okay. So for example, this is the velocity of the exhaust. of the rocket. Okay, so usually it's going to be supersonic. The exhaust is supersonic. So what we want to do is we want to do momentum conservation of this system. So what is the initial momentum of this system? Well, initially we have a mass m moving at speed v naught. So the initial momentum is m v naught. The final momentum is the momentum of the rocket plus the momentum of the exhaust. So that's going to be the momentum of the rocket is going to be m plus dm times v naught plus dv. The momentum of the exhaust is going to be negative dm times v initial minus v exhaust. Okay? And the initial momentum has to be equal to the final momentum. So now what I'm going to do is I'm going to FOIL these terms. I'm going to multiply the terms out on the right-hand side. So I have minus dm times v naught plus dm times v exhaust plus m times v naught plus dm times v naught plus m times dv plus dm times dv. So I foiled that out. Okay. And what we'll notice is that there are a lot of things canceling. Okay. mv naught is here. mv naught is here. So those cancel. dmv naught minus dmv naught. Those two cancel. Okay. dm times dv. Well, so dv is a small number and dm is a small number. So if we take a small number times a small number, it's going to be a really small number. Okay? So this term is approximately 0. We're going to neglect it. Okay? So what do we have left over? We have 0 equals dm times the velocity of the exhaust plus m dv. All right. So now what I'm going to do is I'm going to subtract this over to the other side. So I have minus VE, and then I'm going to divide both sides by m. So I have minus VE dm over m equals dv. And remember, velocity of the exhaust is a constant. So now I integrate both sides from initial to final. Now, the integral of dm over m is natural log. So this integral is going to be natural log of m final minus m initial times the velocity of the exhaust times negative 1. And here I have v final minus v initial, which is delta v. Okay, I'm going to take the minus sign in. So velocity of the exhaust is natural log times natural log of m initial over m final is the change in velocity of the rocket. Okay? Sweet. So this is a very famous equation that I just derived. It's called the rocket equation. It might be called the Tsiolkovsky rocket equation. You can look it up. And it's used by NASA. It's an application of momentum conservation. It's used by NASA. So how do we get the biggest change in velocity of a rocket? You want the rocket to squirt out exhaust at the highest speed possible. The greater the exhaust speed, okay, the greater the exhaust speed, the greater the change in velocity that you're going to have, okay? Also, you want the rocket to lose a ton of mass worth of fuel. We can see that there's a logarithmic relationship here. So, what if M initial is 5 times M final? Okay. Then that means you're going to multiply your delta V by the natural log of 5. You get what I'm saying? So if you've ever seen a graph of the logarithm function, it kind of looks like this. And so what you get when you're doing a rocket is you get diminishing returns. Have you ever noticed that when the space shuttle was launching, it's basically, when it's sitting on the launch pad, it's mostly fuel. Most of its mass is fuel, okay? Because in order to get enough velocity to get into orbit, you have to have M initial over M final be huge, okay? So that the natural log of M initial over M final is enough to get a big delta V, okay? So this logarithm is one of the great challenges in space travel. It's because the logarithm function is so flat, okay, that you have to have M initial over M final be huge in order to get more delta V. Because that's the name of the game in space travel, is you want as big of a delta V as possible, okay? So I hope you enjoyed that little theoretical exposition.